In this video, we're going to explore the concept of a confidence interval for a mean using a simulation from the Russman and Chance aptly collection to help us understand a point estimate, a margin of error, a confidence level, and the sampling distribution of means. So, let's use the scenario of life expectancy. In the US, the life expectancy is 75.5 years currently. And so we're going to simulate a population of say, death certificates that average out to 75.5 years. So for the statistic here, we're going to switch this to means. For the distribution, we're going to assume that one's one's number of years they live is normally distributed, and we'll leave the method as z with sigma. The population mean is 75.5, and we'll assume that the standard deviation of how many years someone lives is 5 years from, on average, from the population mean. Okay, so what we're going to simulate is sampling, say a sample of 25 death certificates, and we're going to use that sample to make an estimate of the population mean. Okay, so this value here is what we are estimating. Now, if we knew that number, and I mean here in this case, we know this number because we're simulating, but in real life we don't know this number, and we use a sample data to give an estimate, or by constructing a confidence interval of the possible values this number could possibly be. All right, so I'm going to go ahead and click sample, and when I do this, you're going to see that we get a sample of, say, death certificates, where the sample mean is 74.6 years, and the sample standard deviation is about 4.7 years. And that's the data. That's the distribution of that particular data, that sample of 25 death certificates. Now, what is going on is that we calculate a confidence interval. What you see here is this green interval, and it generates a left endpoint, or the lower limit, and the right endpoint, the upper limit. Right in the middle is our point estimate. That's the sample mean of 74.6. These are the values that fall between these two numbers here, the left and right endpoint, are the most plausible values that the true value of 75.5 is. Okay, so when we do this in real life, we don't know what the true value is, so all we know, it falls between this and this with so much confidence. The way that confidence interval is constructed is taking that sample mean and adding and subtracting the margin of error, and that's how you get the lower and upper limit. Now, what you notice is this vertical line here is the population mean. So notice it captures the mean. Our interval captures the mean because the line goes through the interval, the green interval. Okay, so that just means it captures it. Now, half the length of the interval is what we call the margin of error. So the length, so from the middle point to either the left or right endpoint here, is the margin of error. And the true value would be the length between the point estimate x bar, right, the sample mean, to the line, the vertical line. That's the true error. Now, that true error is always going to be smaller than the margin of error. And to illustrate this, let's go ahead and use this file that I created in Excel. Okay, so basically what I'm going to input here is my lower and upper limit, and it's going to calculate our sample mean and maximum margin of error and the true value and the length of the interval. Okay, so and let's just go ahead and input this number. So 72.649 and 76.569. Where's our lower and upper limit? So let's go ahead and hit enter. So you can see that matches up with our sample mean, because it's basically the midpoint of this interval. And the margin of error is just half this length of the interval. Okay, so you can see the margin of error is 1.96. 1.96. So that's our margin of error. And the true value, or the true error, which is just the point estimate x bar minus the population mean, and then taking an absolute value because it could be positive or negative. Okay, so this number, the true error, and this number is always going to be less than the margin of error. Okay, so let's go ahead and generate another confidence interval. So in other words, let's go ahead and pull another sample of 25, say, death certificates and calculate a new confidence interval to estimate the life expectancy of an individual. Okay, so let's go ahead and click that button. And you can see that our next confidence interval gave us a new sample of 25, where this time the mean was 75.173 years. Standard is about 4.02 years. And so based on those numbers, we take the sample mean and add and subtract the margin of error. There's a formula for this margin of error you'll see in the notes. But that's how they're getting these numbers. But the point here is trying to explain is that we captured the mean, and the maximum margin of error should always be bigger than the true value, or I keep on saying true value, but the true error. Okay, so let's go ahead and punch in those numbers: 73.213 and 77.132. Okay, so therefore their point estimate once again is just that. The margin of error, notice, didn't change. Okay, it's still 1.96 for this particular procedure. Okay, and the true error, which is 0.328, is actually smaller than the 1.96. This should always be the case if we captured the mean. So let's try that again. Let's generate another sample of 25. So here we got a new green interval which captures the mean, and so let's punch in the numbers here to see that the maximum margin of error is bigger than the true error. So 74.519 is the left endpoint, and 78.439 is the right endpoint. And there you can see the error, true error, is 0.97, but it's smaller than the maximum margin of error, 1.9, about 2 years, right? Okay, do it one more time. Got another sample of 25. This time, though, we got a left endpoint or lower limit of 73.130 and 77.050. Okay, so we got a point estimate of 75.09, right? 0, that's our sample mean. Once again, maximum margin of error stayed the same. So what you see is that the true error is always going to be smaller than the maximum margin of error. Now, keep in mind, we never know the true error, and therefore, when we do these procedures, we only understand what the maximum margin of error is, and we just know that our maximum margin of error bounds the true error. Okay, so it gives us a sense of how good our estimate is. All right, now this procedure is based on the standard normal curve, and sometimes we just get samples that are not reflective of the population, which means that we're going to get a horrible estimate. Okay, that's because of just sampling error. We just get a bad sample. I like to say a bad sample mean. And so let's go ahead and click another button here to generate another sample. And I'm going to keep on doing it until I generate a bad sample. Eventually, I'll get one. And you can see the procedure is pretty good. Oh, there you go. It typically gives you good samples, but here I got a bad sample. How do I know that? Well, the confidence interval, my sample mean of 72.73 gave me a data set or a sample that was not too reflective of the population. Okay, and let's observe why this is a bad sample or bad confidence interval. Well, you can see visually it does not contain the true value of the mean. right? We see that it does not contain the true value of the mean. It's to the left of it, which means our upper limit is smaller than that. Okay, so when we punch in our lower limit here, we're gonna get 70.813 and 74.733. I get a point estimate of 72.73. That's like before, that's true. But what do you notice about the true error? The true error actually is bigger than the maximum margin of error. And so when this occurs, we get that when we get a bad sample, the true error is too large, larger than our maximum error. We could see that here. And well, that just happens by the nature of this procedure because we got a bad sample. Okay, let's see if I could convince you of that by drawing another sample that has a red interval. There's one right there. And so if I plunge in 75.1519 and 79.439, you can see this time our true error is slightly bigger than our maximum margin error, but we still got a bad sample. And so that's why we're not capturing the true mean. Now, why does this happen? Why does this happen? Well, it's because we are constructing a 95% confidence interval, and there's a chance that we generate a bad interval because of the sample. So to illustrate this, we're going to do this many times. So instead of doing one sample at a time, let's generate, say, 1,000 samples. Well, let me generate maybe 100 first and show you what I mean. Oops, sorry, I changed the sample. That should be the sample size will keep the same. What I want to do is generate 100 samples of 25, and for each one of these samples, we're going to simulate calculating a confidence interval. All right, so let's go ahead and sample, and what you're going to see here is now 100 intervals, and this is the last sample that was generated. But what you see down here in the sample statistics is what we call the sampling distribution of means. Or more specifically, sampling distribution of sample means. And so that's we should notice the shape. The shape is looking mound shape because that's what the central limit theorem tells us that it's going to look like. And over here is all the confidence intervals. Now notice the majority of the confidence intervals are green, but there's some that are not green. So in this case, 1, 2, 3, 4, 5. 5 of these confidence intervals are bad confidence intervals in the sense that they don't capture the mean. They were generated from bad sample means. And what does this have to do with confidence level? Well, we did this 100 times, and if you look over here at the results here, 95 out of the 100 sample means we generated, which is 95%, is the confidence level. So when you do this procedure many times, that confidence level, 95%, means 95% of the confidence intervals will capture the true mean using this procedure. If you're questioning what's the running total here, it's just that I was clicking on the button before this several times, and that's just the running total. Since we're doing it, a simulation here, well, 117 out of the 124 intervals captured the mean. And so that 94.4 is just the estimate for the confidence interval. Sorry, confidence level. Okay, but so to see this here, notice the distribution here. It's mound shape. Now to get a better or clearer picture, let's go ahead and now generate 1,000 confidence intervals, or based on 1,000 samples means. So we're going to click this in here. So instead of doing one by one, we're doing 1,000 at one time. Let's click sample, and you can see there's a whole lot of green. And you can see our sampling distribution of means is filling out more like a normal curve. Okay, so once again, well, this 950 out of the 1,000 is what's expected. Now this is a simulation, so this won't always hit 95%. It should be close to 95%, but doesn't necessarily have to be. It'll be more like the running total here. Okay, and so that's the confidence level. Confidence level is the proportion of confidence interval that will capture the true mean when you do this many times for samples of the same size. So here we're doing it is for samples of 25.